Welcome you all to part 5 of Nuclei, that is half-life. If you consider a single person, you cannot tell when he will die. But if you consider a group of 50,000 people, we can make certain approximate prediction that these many percentage of people will die before 50 years of age. It is similar to if you take a single nucleus, you cannot tell when it will decay. What happens to it after 1 hour? But if you consider group of nuclei, we can make certain approximate predictions now here, right? So that predictions we'll be doing in the session here, right? So let us begin with the half-life. If the number of nuclei in a radioactive sample is N0, and after 1 hour, this number of nuclei reduces to half, that is N0 divided by 2. And again, after 1 hour, this number of nuclei again reduces to this number of nuclei, that is N0 divided by 2 reduces to half, that is N0 divided by 4. And the time during which the number of nuclei reduces to half, and that time is called as half-life. That is time during which number of nuclei of a radioactive substance reduces to half of its initial value is called half-life. And half-life of different nuclei will be different. It varies from microseconds to billion of years. For example, if I'm taking a radon 224, the half-life of this is 55 seconds. In 55 seconds, these many number of nuclei of radon 224 reduces to this number many of nuclei. In the similar manner, if we consider carbon 14, it has the half-life of 5,730 years, and these many years it takes to reduce this number of carbon 14 to this number of carbon 14, and that time taken is called as half-life. Let us understand more about half-life graphically. We have from law of radioactive decay that n is equal to n0 e raised to minus lambda t. It shows that the graph must be exponential decrease now here. That's why we have the term e raised to minus lambda t. That's why the graph is exponential and decreases. Let us consider this is the number of nuclei, initial number of nuclei, n0 now here, right? It reduces to half, that we take n0 divided by 2. And if we consider what is the time taken, that the time taken will be t half. Right, and again, if I reduce n0 divided by 2, n0 divided by 4, the half of this now here, again if I take, it will be getting with the second t half, the time duration will be the same as we got earlier now, right? Again, if you reduce n0 divided by 4 to, again n0 divided by 8 now here, if I take the graph, again we will be getting the same time duration, and this time duration at which number of nuclei reduces to half, and that time duration is called as half-life. And now let us derive the expression for half-life. Okay, there is derivation of half-life. Let us consider a radioactive sample here, right? And in that sample, let N0 to be the number of nuclei at a time t equal to 0. That is initial number of nuclei. And after time t, the number of nuclei reduces to n. Right? From law of radioactive decay, n is equal to n0 e raised to minus lambda t. Right? So when the time will be half-life, that is t is equal to t half, number of nuclei reduces to half of the initial value, that is n is equal to n0 divided by 2. Let us substitute this in this equation. So we will be getting with n0 divided by 2 is equal to n0 e raised to minus lambda. In place of t, I will be writing it as t half. Right? Now n0 will get cancelled. We will be getting with 1 by 2 is equal to e raised to minus lambda t half. Since it is e raised to minus lambda t half, we will be making a reciprocal of it to get positive here. Taking a reciprocal, so e raised to lambda t half is equal to 2. Since we have an exponential term here, we will be taking ln on both sides. Taking ln on both sides, ln e raised to lambda t half is equal to ln 2. We know that the formula, that is log x to the base b. The formula is b log x. In the similar manner, ln e to the lambda t half is lambda t half ln e, that is equal to ln 2. The value of ln e is 1, the value of ln 2 is 0.693. We will be getting the expression lambda t half is equal to 0.693, and t half is equal to 0.693 divided by lambda. So this is the formula for a half-life, that is t half is equal to 0.693 divided by lambda, where lambda is decay constant. And one thing what you need to note here is the n0 value get cancels, means the half-life does not depend upon the initial number of nuclei. So the expression for half-life is t half is equal to 0.693 divided by lambda, where lambda is decay constant. Now let us begin with the mean life, that is tau. If you consider single nucleus, you cannot predict will it decay in the first half-life or will it decay in the second half-life. So we'll be moving on to the mean life. That is, we will be taking the average. What is the average? Sum of lives of all the nuclei divided by total number of nuclei. So that is what the mean life is. It is the ratio of sum of lives of all the nuclei to the total number of nuclei. If we calculate this, we will be getting the expression that tau is equal to 1 divided by lambda, and this is the expression for mean life, and the lambda is decay constant. Now, we will be finding what is the relationship between these two, that is half-life and mean life. We got half-life as 0.693 divided by lambda and mean life as 1 divided by lambda. If you see these two and if you compare these two equations, we will be getting the expression that T half is equal to 0.693 into tau, where T half is half-life and the tau is the mean life. By this, I can conclude that mean life is greater than T half. So this was all about half-life and mean life.